Okay, folks, there was one like this posted on Michael Penn's channel that created a little bit of controversy. His problem, I think, was 4n squared. And some of the viewers thought it was more like a continuous, like x approaches infinity, that wasn't made clear that n was a natural number. But this is definitely the case where n is a natural number, you know, a natural number being 1, 2, 3, 4, 5. And so these are discrete points which create a sequence. And the question is, does this sequence converge? Now, thinking of it as a continuous variable, it sure looks like it's just a sign of infinity, which is oscillatory and doesn't make sense. But it's actually, you're talking n equals 1, n equals 2, n equals 3, create separate discrete terms of a sequence. Now, so what's going to make this fly is, and I'll do this, all the work is on the next page, but what really is useful right here is the result that the sine of any angle, in other words, we're going to use the periodicity of the sine function. The sine of, and this is the same is true for cosine, but the sine of any angle, usually we're talking radians, is equal to the sine of that angle or that real number plus or minus any multiple of 2 pi, any integer multiple of 2 pi. I'll call that 2n pi. Okay, like that. Now, for this particular problem, it's going to be convenient to use 4n. I mean, if it's periodic 2n pi, it's going to be periodic 4n pi also. So that's what's going to happen on the next page. So let's go to the next page and take a look at how we exploit that. Now, so here was our problem. Here's the original problem. Now, what we do, let's see, can I get that? No, I guess I have to do the whole thing. But what we can do is this takes advantage. You see how the pi gets factored out? And this would actually be pi times 4n right here. Now that's useful because I'm doing a slightly different version of things. I'm doing 16n squared instead of 4n squared like Dr. Penn did. And so anyway, this, if you take a look here, this is just pi times minus 4n, which would be that periodicity constant that you can add or subtract to sine. All right, now the next idea here is to use this conjugate trick. And notice we could have used plus 4n right here, and this would have just been a minus right here. So that doesn't make any difference. Either way would have worked. Now, what makes this work out nicely is you can think of this part right here as being a minus b right here. And then this piece on the other side. See, half of math is multiplying by 1 in kind of a cleverly disguised way. But you see, just in the numerator, this would be a squared plus a squared minus b squared, right? Now, I guess I sort of left out a step, but what's going to happen right here, a squared minus b squared is actually 16n squared minus 16n. Y'all hang on just a second. I'm getting my power working back here. Okay, back in business. Okay, now, whoops. Here we go. Okay, sorry about that. I almost ran out of power. All right, but y'all see what happens here? You would, when you multiply through by, this is the a plus b version of this, and when you multiply through, the 16n squares will actually cancel, and you'll just be left with minus n here. Again, just in the name of avoiding clutter, I left that part out, but again, your a squared minus b squared would be 16n squared minus 16n squared. And so they cancel out, and you're just left with this n right here. And then I carried the minus sign out to the front here. Okay. Now at this point, what we have here, it's just a limit, and these n's will cancel out. And since sine is a continuous function, you can actually take the limit inside here. And so notice that the n's cancel out, as n approaches infinity, this piece right here is going to approach 0. This piece right here is going to approach 0. And so you're going to end up with the sine of minus pi over 8. All right, now it turns out that has a closed form, and its decimal equivalent is this figure right here, 0.3827. Now what I want to do is just go up, so this will make some sense. I'm going to go up and actually try it out for just a value of n and see how close we get to this 0.3827. So let's back up here. Let's see here. Yeah, again, what I'm going to do is pick, and you don't have to really go that large. It's sort of surprising. Let's just try n equals 10. Okay, you wouldn't think that would be big enough. I mean, this does say n approaches infinity. Let's try n equals 10. Okay, n equals 10. Now, so the limits get removed, and what you have right here is the sine of you'll have the sine of pi. Y'all, again, if you'll allow me to do the arithmetic here, I picked an easy one. 10 squared is 100. 16 times 100 is 1600. And so what you would have right here is the square root of 1590, it turns out. 1590. I'm double checking it right now. 1590. Again, folks, for n equals 10. 10 squared is 100, 16 times 100, 1600, 1600 minus 10 is 1590, and it's still the square root. All right, now it turns out, and let me just, if you'll give me just a moment, I'm going to check this just on the calculator. You end up with approximately minus 0.38. See what we got here. 0.3825. Okay. You know, sorry I can't keep this on the same screen, but for n equals 10, which isn't that large, right? This says as n goes to infinity, but already at the 10th, this is really, you can think of this as a sub n. If you really, you know, you're used to seeing this a sub n notation. A sub n is approximately equal to this value right here. So it's just the 10th term in a sequence, right? It's equal to this value. So let's keep that. What I had, point minus 0.38. That's actually a not, well, yeah, it is. It makes a little bit of difference here. There's a 3 right there, y'all. Sorry about that. It's 0.38325. Okay, so let's take a look at the next screen. Okay, that'll just stay on the screen, I hope. Yeah. Hey, good. Okay, this is one time where I'm glad it stays. So y'all, you see how close that actually is to this exact value? Here you have minus, I should have put a minus sign in there somewhere, but that's a minus 0.3827. This says 0.38325. Okay, so you see it's a pretty close approximation just for the 10th term. All right, folks, hope that made sense. Let me know what you think. Have a good day.